So integration is the second pillar of calculus, and it is known as the anti-derivation or antiderivatives, and it is a way of undoing whatever differentiation has done. So because of the time constraints we have, I think the best thing for us to do is to go straight to the point without having to do too much of the theoretical aspect of integration. And so basically, like I said, it is anti-derivatives. And generally, the basic techniques of integration are as follows. One is the reverse power rule. That is, the power rule in derivatives or in differentiation is if the derivative of x to the power of n, we know that to be equal to nx raised to power n minus 1. So we subtract and we multiply in differentiation, but in integration, we do the opposite in the reverse order. So the integral of x to the power of n with respect to x, so integral of x to the power of n with respect to x is equal to x to the power of n plus 1 over n plus 1, then plus c. This is only true when n is not equal to negative 1. So when n is equal to negative 1, so when n is equal to negative 1, that is integral of x raised to power negative 1, which is the same thing as integral of 1 over x, is the natural log of x. Okay, then of course we know the basic fact from um, from differentiation that the integral of sine x is going to be negative cosine of x, since the differentiation of cosine of x is sine x. So with respect to x is negative cosine of x dx. The integral of cosine of x with respect to x is equal to sine x. Also, we have the fact that when you have the integral of a constant times a function with respect to x, you can pull out the constant. We also know that the integral of a sum, f of x plus g of x with respect to x, is the sum of the integrals, f of x dx plus g of x dx. I know many of you already know all these things, so I'm just for formality's sake, while we gently go into the real business. Also, which one is particular here? All right. As we continue to look at things, we will come back to add more to this. So the basic things that we'll see is U substitution, then you talk about integration by parts. You talk about integration by partial fraction. I will talk about trig substitutions. Yeah, these are the main things you use with integration. So sometimes you also have to do some long division and some algebraic manipulations. So unlike differentiation, that is straightforward when you see a question. For integration, sometimes you have to, you know, you do, it's not direct. It's not what you see. What works for something will not work for something that is slightly, just slightly different. For instance, these three things, x times e to the x, then x times e to the x squared, then um, e to the x squared. Let me negative x or x squared. Let me just put x squared. These three things, they look alike, except for the fact that, okay, the third one does not have e, but they they require different techniques of solution. That's why integration is wild compared to differentiation. When you see something, you already know what to do. So it's a nice skill to be able to identify the appropriate technique to use when you want to integrate. So most cases, when you see a product, when you see a product of two functions in derivatives, you know it's going to be a product rule. But in integration, the first thing that should come to your mind is, can you make a good U substitution? Why do I keep spelling substitution like this? If U substitution is not something that will work, the next thing will be, can I use integration by parts? So those are the major two things that you think about when you see a product. So for instance, these two functions, the first one, you cannot use U substitution. The second one will be U substitution. So why can't we use? Yeah, is there a question? In, Yinka, what's the question?
Um, there is no question, sir.
Okay, okay, okay. I thought you're muted to ask a question. All right. So the second one, U substitution will work. The first one, U substitution will not work. So the first one will be integration by parts, and the second one is U substitution. While the third one is a different beast on its own, it is the hardest of the three of them, even though it looks the simplest, because there is nothing that will cancel out. So this is a Gaussian integration, and it's something beyond the scope of maths 102 or 121 as you call it. So when you see a product, these are the two things that should come to your mind. When you see a quotient, again, first thing is to see whether it can be simplified. So when I say simplify, I mean something like, if you have a plus b over c, can you split it up into a plus b, a over c plus b over c, or things like that? Second one is to think about, so check whether it's a proper fraction or an improper fraction. So if it is what do I mean by a proper fraction? A proper fraction is when the degree of the numerator is less than the degree of the denominator. But if it is an improper fraction, for an improper fraction, you have to, think about having long division first before you think about something else. Then the next thing is U substitution. Then you can also have what else can we do? Integration by partial fractions. This is where partial fractions come in. Then you can have trig substitution. So in no particular order, anyway. You know, trig substitution and some other algebraic manipulations. All right. So okay, then when you see trigonometric functions, we are looking at different trig identities. Is very, very important. Trig identities, conjugations, and and what have you. Good. So enough of the story. Let's get down into business. I'm going to start with the. Okay, let me see. Okay, the questions from the 2024 year. Just hold on. Let me fetch it. Okay, found it. Save. Okay, so I'm not going to do it in any part. I'm going to just continue, from the first question. Crop. Okay, so before we continue with the integration question, you can see the test itself. There is just one question that is not an integration question. So most of what you are going to come across in this course is going to be mostly limits and integration, unless things have changed drastically. So it's mostly going to be limits and integration and a little bit sprinkle of differentiation. So before I continue with the integration question, does anybody have any issue with number one?
Yes, sir.
So is it, do you want us to go over the number one question? Is that what you're
Yes, sir.
saying?
Yes,
All
sir.
right. That's okay. So number one question says that given that y equals to, y plus cos squared y cubed is equal to sine 5x squared. The question is saying evaluate the slope of the curve. Find slope of the curve at this point, square root of pi over 10, 0. Okay, so slope of the curve, this function here represents a curve. The slope of the curve is simply the derivative of the curve. So if we call this, if this is f, capital F of x comma y, the slope of the curve is the derivative of the curve evaluated at a particular point. So in this case, it's evaluated at square root of pi over 10, 0. So we need to take the derivative of this function. And this function is defined implicitly. So what do we mean by implicitly or explicitly? So when I write y equals to 2x squared minus sine x, this is a function that is defined explicitly in terms of x. But when you look at this function here, it is impossible for you to write it, as a function of, you cannot write y as a function of x explicitly. Everything is mixed up. It's an implicit definition. So the y's and the x are together. So to take the derivative of something like this means you have to differentiate both sides of the equation. So you want to differentiate y plus cos squared y cubed. And you also want to differentiate sine 5x squared on the other side. So, and this means, although what I'm writing is formality, but this means you differentiate y with respect to x, you differentiate cos squared y cubed with respect to x, and you differentiate sine 5x squared with respect to x. Okay? So the differentiation of y with respect to x is just dy dx. That is what it means to say dy dx, the differentiation of y with respect to x. And the next term here, so let's look at it separately. So ordinarily, if you have y, so let's build it up little by little. Or maybe I should start with the right-hand side. If I have y equals to sine, okay, let's start with sine x. Differentiation of sine x is just cosine of x. But if there is a composition of a function with sine x, so if I have y equals to sine f of x, we are supposed to use chain rule here. And chain rule, the application of chain rule is that the y dx is the differentiation of the outer function. The outer function here is sine x. So the differentiation of that is cosine of f of x, then times the differentiation of the inner function, f prime of x. So if y equals to sine 5x squared, we are going to do the y dx is equal to differentiation of sine, which is cosine of 5x squared, times the differentiation of 5x squared, which is 10x. So that is 10x cos 5x squared. So if you have three functions embedded together, for instance, if I have y equals to sine of e to the power of 5x squared instead, you start from the outer one, then you go layer by layer. The y dx is equal to the differentiation of the outer function is cosine of e to the power of 5x squared. Then the next layer is e to the power of 5x squared. And that one is also chain rule. The differentiation of e to the power of 5x squared is 10x times e to the power of 5x squared. So that's the differentiation of the second layer. Okay, so that has already given us the third layer implicitly. So it means this is equal to 10x cosine of, or 10x e to the power of 5x squared times cosine of e to the power of 5x squared. Again, don't forget, if at any point I have said something that you do not understand or have made any mistake, you can interrupt me for clarification. So we know the right-hand side from what we have just discussed here to be 10x cosine of 5x squared. Now let's do the same thing with cos squared y cubed. So first and foremost, I'm going to use x cubed first. So similarly, if I have y is equals to cos f of x, then the y dx will be negative sine of f of x times f prime of x. So you don't need to spend too much time trying to write things down. Okay, I'm going to send out this PDF at the end of the session. So the important thing is for you to try to listen and try to get what I want. And I encourage you to ask questions because I'm ready to go over it again. So negative sign of f of x times f prime of x. So if I have y equals to cos x cubed, then the y dx is going to be equal to negative sine of x cubed times the derivative of x cubed, which is 3x squared. So the answer will be negative 3x squared sine x cubed. All right. So what if we now have y equals to cos squared x cubed? Y equals to cos squared x cubed is the same thing as cos x cubed everything squared. So the outer function here is a function that looks like y equals to x squared. So the derivative of the outer function is 2x. So that would be 2 times cos x cubed. Then the derivative of the inner function is cos x cubed. We have done the derivative of that in the previous step. That is times negative 3x squared sine x cubed. So this is negative 6x squared cos x cubed sine x cubed. I can actually play around with that, but don't let us do that, not to confuse you. So we actually know that 2 sine x cos x is equals to sine 2x. So 2 sine x cubed cos x cubed should actually be equals to sine 2x cubed. So optionally, I could have written this as negative 3x squared sine 2x cubed. It's the same thing. Yeah, it's the same thing. But now it is not x. So at this point, are there any questions? Is there anybody that does not understand what we have done on this right-hand side? So the derivative of cos squared x cubed. Is there anybody that does not understand that? Is it clear to everybody?
Clear, sir.
All right, good.
Yes, sir.
Good. So if it is now y cubed instead of x cubed, the idea remains the same. But this time around, we are going to consider, so let's do cos f of x. So we have already done cos f of x. So we said the derivative of this is, that's what I've written up here. So it means if f of x is y, then it means, I cannot use y here. So let's say this is p. Then it means the p dx is negative sine y times the derivative of y, which is the y dx. So we are just using the chain rule all over again. So when you have y squared here, so what is the derivative of y squared? Y squared is like f of x squared. So to use chain rule here, the outer function is like x squared. So that is, so if y is equals to this, the y dx is 2 times f of x, then times the derivative of the inner function, f prime of x. That is chain rule in action. So if I have y squared, I want to differentiate y squared. It will be the same thing. it will be 2 times y times the derivative of y. Why have I shown that? Because we are going to need it for the derivative of cos y cubed. So what's the derivative of cos y cubed? The outer function is cos. So this will be negative sine y cubed. The inner function is y cubed. So which is like this one that we did here. So if it is f of x cubed, it will be 3 times f of x squared times the derivative of f of x. Okay, that is chain rule. The derivative of the outer function times the derivative of the inner function. So in this case, when we differentiate y cubed, we are going to get 3y squared times the y dx. So that is the differentiation of cos y cubed. So it's like we are combining 3 functions. Cosine y cubed. Okay, 2 cosine and y cubed. So negative sine y cubed times the differentiation of y cubed, which is 3y squared dy dx. Now, the one that we need is cos squared. This is the one that combines 3 functions. Cos squared y cubed. So the outer function is the one that looks like x squared. So to differentiate x squared, we know it is 2x. So the outermost function, if we differentiate that, we have 2x. So that is 2 times cosine of y cubed. The inner function is what we have done here. So that will be equal to, so put it beside it. That is times negative sine y cubed times 3y squared dy dx. So combining these together, we are going to get, so I just want to copy this to this part. So that will be negative 6y squared cos y cubed sine y cubed dy dx. So I've just copied what is here to substitute what we have here. Any question? I assume not. All right. Then the next thing is for us to get dy dx. So on this part, I can factor out dy dx. I'll get 1 minus 6y squared cos y cubed sine y cubed is equal to 10x cos 5x squared. Then dy dx, so I'll divide both sides by the coefficient of dy dx. So this is 10x cos 5x squared over 1 minus 6y squared cos y cubed sine y cubed. So this is the derivative of the given curve. Then to find the slope of the curve at this point, so at the given point, square root of pi over 10 comma 0. So this is y, x, this is y. The slope will be, so we substitute this for x and that for y. So it will be 10 times square root of pi over 10 cosine of 5 times pi over 10. Why is it 5 times pi over 10? Because pi over 10 squared is equals to pi over 10. So instead of 5x squared, we have that. Everything divided by 1 minus 6 times 0 times whatever. I'm not going to, okay, let me just write it to fulfill righteousness. So cos 0 cubed sine 0 cubed. But we know that 6 times 0 times anything is just 0. So that denominator is just 1. And the numerator, this is going to be square root of 10 pi times cos pi over 2. And what is cos pi over 2? Cos pi over 2 is 0. So this is square root of 10 pi times 0. So everything is equal to 0. How did I get square root of 10 pi? 10 times square root of pi over square root of 10. And 10 is the same thing as square root of 10 times square root of 10. So this cancels this. We are left with square root of 10 times square root of pi. And that is square root of 10 pi. And cos pi over 2 is 0. That's because 90 is 0. So the whole answer is equal to 0. Any question before I continue?
Yes, that is a question. So this type of question now relates to like minimal and maximal, like all these local extrema and such like that. All right.
Something like that. So this one is not actually, so this is, well, we can say it is an application of derivatives, but it is not optimization. You are not looking for minimum or maximum here. Because
So like the
this is just asking for the slope. This is not asking for the minimum or maximum value. We're just asking for the slope at a particular point. So you find the derivative, then you substitute the point that you are given in the derivative. If you are looking for maximum or minimum point, you find the derivative, but you have to now set the derivative equal to 0 first to solve for x. That will give you the critical point. So the critical points are now the candidates for the maximum or the minimum point. So the difference between that and this, okay, so to get slope of a curve or f of x comma y, find the derivative okay, and put in or plug in the given points in the derivative, and that's all. Okay, because f prime of p is simply the slope of the tangent line to f of x at the point x equals to p. But to optimize, that is, either minimize or maximize a function, so A, you obtain f prime of x, that is dy dx. 2, you set it equal to 0 and solve for x. So this gives the critical points. Then you plug in the critical points, this obtained x, into the original function not into f prime of x. So when you are doing minimum or maximum, you plug in back into the original function and not into the derivative. Unlike when you are looking for the slope, you plug in the given values, given x and y, inside the derivative. Is that clear now?
Yes, sir. Sir, can you just give a question? Just write it down so I can like solve it and send it to you later. Thank you.
On minimization?
Yes, this is minimization. Maximum and minimum. Yeah, is it the same thing?
Oh, no, on the optimization. So hold on.
Yes, sir.
Let me get a question from this quiz that I gave my students not long ago. Okay, so here that should be midterm. Should be midterm 2. Hold on just a little bit. Okay, found it. Okay. Yes, it's just a simple question. So I'll send it. Oh, let me just put it here. Hold on. Come here. I've sent it to you on WhatsApp. Control V.
Thank you, sir.
Welcome. Control V, and maybe I can also just put it here. All right, so we can now continue with the integration bit. Okay. So the next integration. So any questions so far from any other person before we continue? All right, so I guess we can go ahead. So the next question here is the integral of x plus 2 over square root of x plus 3. Square root of x plus 3 dx. Okay, so this is a quotient. This is a fraction. And it is not something that you can split easily. So, and of course, there isn't always one way to solve integration. But for me, what I would do here is to go with u substitution. And that is the easiest way to think about this. So the appropriate u for most fractions will be something related to the denominator. I said most, not all. There are many that are not the denominator. So here we say let u be equals to x plus 3. The idea of u substitution is identify the u, and the next thing, get an expression for the u dx. So in this case, the u dx is 1, so it means the u is equal to the x. Then we want to rewrite the whole expression in terms of u. So if this is the original integrand, so this will be over square root of u, then dx is now du. But we don't want any x at all in the expression. So how do we cater for that? We know that x plus 2 is the same thing as x plus 3 minus 1. And x plus 3 is u, so it means our numerator will be u minus 1. if you cannot think of it that way, if u is equals to x plus 3, then x is equals to u minus 3. So if x is equals to u minus 3, then x plus 2 will be u minus 3 plus 2, which is u minus 1. In both cases, we land on u minus 1. Any question about that? So who knows what the next step should be here? What can we do next year? Can anybody give us a suggestion? Yeah, Jay. No, Joy. You can unmute yourself and talk. Joy, oh, you can unmute yourself and talk. Joy, are you still there? All right. I'm going to assume she raised her hand by mistake. Okay. So does anybody have an idea of what we can do from here? How can we go ahead with it?
I think we can differentiate, but I don't know.
So you remember what I said to do when we have a quotient? When you have a plus b over c, when you have a single expression in the denominator. So I can see Joy is typing. So when you have a single expression in the denominator, you can actually split it up into a over c plus b over c. So, and in this case, we have u minus 1 over the square root of u. So it means that I can actually split it up into u over square root of u minus 1 over square root of u. Okay, so the u substitution. So that's what we want to go over carefully now. Yeah. So anytime you need to talk, you can just type it in the chat if you don't have access to the audio. Okay. So we started with, let me go over the u substitution again if that part is not clear. Let me go over it a little bit slower. So there are two things here that we could have made the u. So we could have said, okay, Elijah, we wanted to say something. You can unmute yourself and talk very quickly.
My question is, sir, you said once you are using product rule, that we can use substitution and integration by parts. And once you are using quotient rule, you can use simplify, partial fraction, use substitution. And this is a like a quotient rule. How do we know that to use substitution? That's my question, sir. How do we
Okay,
identify
good.
that the next thing is use substitution once it
Okay,
is
good.
quotient?
So first and foremost, this is not quotient rule or product rule. So this is just a product. This is a quotient. So that's the first thing I want to clear out of the way. So it is a quotient. When I say quotient, I mean a fraction. And when I say product, I mean, product of two expressions of x. So we can use different things. So for this particular quotient, so if you think about it, so I said we can simplify. So, and the simplification I mean is, if you have, for instance, if I have x squared plus 2x minus 5 over square root of x, something like this, or over 3x cubed. If you have something like this and you want to integrate, this one you can simplify algebraically. I mean, you can split it into x squared over 3x cubed plus 2x over 3x cubed minus 5 over x cubed. Okay, then each of these can now be broken down. So x squared over 3x cubed is 1 over 3x. 2x over 3x cubed is 2 over 3x squared. Then you have minus 5 over x cubed. So, and then this one will give us, because that is just 1 over 3 integral of 1 over x, 2 over 3 integral of x raised to power negative 2, minus 5 integral of x raised to power negative 3. And that will be 1 over 3 natural log of x plus 2 over 3 x raised to power negative 1 over negative 1 minus 5 x raised to power negative 2 over negative 2, which is just 1 over 3 natural log of x minus 2 over 3x plus 5 over 2x squared plus c. That will work for a case where you just have a single expression in the denominator. But if this was 3x cubed plus x squared, then I won't be able to split it this way because it will not simplify things. Then I have to think of something else to do. And the next thing, if you cannot simplify, the next thing that you should think of, the next order when you are dealing with fractions, is U substitution. So when will a U substitution work? U substitution will work when you see that whatever you are considering as U, when you take its differentiation, it is going to give you something related to what you have in the other part. It is going to help us to cancel x totally. So the idea of U substitution is to be able to eradicate all traces of x and work with U totally. Okay. For instance, in this particular question, this particular one, so maybe we should do that. So let me clear. So before we come back to the one we are doing, so let's do this one. It looks interesting. Is this something I can do? I don't want to set a trap for myself. So let's see. If I split that, it is going to lead into some partial fraction eventually, and I don't want to go into that. So let's say, let me remove the, so we have 3x cubed plus x squared minus 5. Let me put the minus 5 in the denominator. So for this one, I know I cannot split it, but I know that if I take the u as okay, I still need to do some adjustments here. So this will give me I don't want to run into trouble. So let's say x cubed plus okay, x cubed plus x squared. If I want to obtain what is upstairs. Okay, let me edit this a little bit. So if this is 3x cubed, 9x squared, and if I make this if I make this x squared, I can make this 2x minus 5. Okay, this will show what I need to get. So here we cannot split, but we know that if I do, this is still not good. This is still not good. If I do 9x squared, I'm going to have a factor of 9 there. So it is better for me to make this equal to This is what we go through when we try to set questions for students. So 9x squared, I want to be able to factor 9 out. Okay, so I will make this 18x. Yeah, I think it should be fine now. 9x squared plus 2x. No. No. If I factor 9 there. Okay. 9 2x. 9 2x. So why am I making it too difficult for myself? Okay, let me just make this 3x cubed plus 5x and make this no, 3x cubed plus, yeah, if I do 9x, I make this x squared plus 1. I think this will work. I can now put the -5 that I want here. Yeah, will that work? Yes, I think it will work. Okay, so why will this work? If we make u equals to 3x cubed plus 9x minus 5, then the differentiation of this is equal to 9x squared plus 9. And when you see something like this, you can see that it is actually 9 times x squared plus 1. So u substitution will work here. But if I tweak it a little bit different from this, we'll run into trouble. You can see how I struggled to be able to generate a question where u substitution will work. And that's one thing about u substitution. Unlike differentiation, I don't need to think too much to be able to form a well-posed question for derivatives. I can be creative as much as I want. But for integration, one needs to be very careful so that you don't even, as a teacher, you don't even run into trouble providing a question for your student. So for the integration itself, when you have a fraction, I know I cannot split this. So splitting this will it's not just one expression in the denominator. But once you have more than one term in the denominator, the first thing you want to think of is u substitution. So, and when does u substitution work? You think about it. If you make the denominator equals to u, if you take the derivative of that, are you going to get something related to the numerator such that all traces of x will be cancelled out? And in this case, it is true because du dx is equal to this. It has x squared plus 1 in it. It means that I can rewrite the x as du over 9. If you make the s subject of the formula, there you get du over 9 x squared plus 1. And that will be, so I can now rewrite this as integral of x squared plus 1 over u times du over 9 into bracket x squared plus 1, such that x squared plus 1 cancels out x squared plus 1. And you can factor out the 9, the 1 over 9 integral of 1 over u du. And that is going to be equal to 1 over 9. So the integral of 1 over u is natural log of u plus c. Then we'll bring back the u, which is 3x squared, all of that. 1 over 9 natural log of 3x cubed plus 9x minus 5 plus c. So with integration, you need to be careful because it is very easy to run into trouble. Okay, so you think about it, you cannot simplify, and you check whether u substitution will work. It is not in all cases that u substitution will work. And the next thing you think of is going to be integration by parts. when you are dealing with fractions. So you first and foremost, whether it can be simplified. Secondly, use whether use substitution will work. Thirdly, whether you can use partial fraction. And another one is whether you can use trig substitution. It goes on and on like that. That is one big problem with integration. So let's come back to. So do you understand this that I've said? Any questioning problem with that before we go back to what we are doing? Elijah, does that answer your question?
Yes, sir. Thank you, sir.
Okay, good. You're welcome. So coming back to this particular one. So, Madam Joy, I hope you are with us now. So looking at this. So I know I cannot split it. Splitting it will mean, or simplifying will mean I want to write something like x over square root of x plus 3 plus 2 over square root of x plus 3. But this even complicates the problem the more here. So the first best thing to do is to just go ahead with the u substitution. So I can say that u is equal to x plus 3 here. So most times when you have expressions under a square root or inside a bracket or inside sign or inside logarithm, these are the things that you make your u. So u is equal to x plus 3. And the u, anytime you are doing u substitution, the first step is identify u. That could be a job on its own. Identify the appropriate u. Next thing is to take the derivative of that u. So the u dx, from which you now obtain the x in terms of the u. Then 3, you rewrite the integrand in terms of u and the u. So it means all traces of x must go away. Then 4, you integrate. 5, you go back to your x. So these are the steps involved in performing u substitution. So in this case, if u is equal to x plus 3, we have the u dx is equal to 1, which means the u is equal to the x. So if we want to rewrite all of these things, we know that what is underneath the square root is what we have made our u. And x plus 2, we want to write it in terms of u. Since we know that u is equal to x plus 3, then it means if you subtract 3 from both sides, x will be equal to u minus 3. Then x plus 2 will be u minus 3 plus 2, which is u minus 1. So this is u minus 1 all over square root of u. Then our dx that was here is now going to be du. So we have changed everything from the u world to the x, from the x world to the u world. Joy, do you understand now what I've just substituted? Okay, I assume that is a yes. Then for us to integrate, we have said the next thing, the right thing for us to do here is to split it up. So this is going to be the integral of u over square root of u minus 1 over square root of u du. And for us to be able to simplify this, what is u over square root of u? It is just square root of u. Because u is square root of u times square root of u. So that over square root of u, the u's will cancel. Or you can think about it as rationalization. So this means this is equal to integral of square root of u minus 1 over square root of u can be written in exponent form as u. So I can write, okay, let me write this step first. Then both of them can be rewritten as u raised to power half minus u raised to power negative half du. So in this case, the integral of u raised to power half, you remember the reverse power rule. The integral of x to the power of n with respect to x is x raised to power n plus 1 over n plus 1. So if I do the same thing here, this is u raised to power 3 over 2 over 3 over 2 minus u raised to power negative half plus 1 is 1 over 2 over 1 over 2 plus c. And that's exactly the same thing as 2 over 3 times u, and our u is x. What is u? X plus 3. X plus 3 raised to power 3 over 2 minus 2 x plus 3 raised to power half plus c, which is the same thing as the square root of x plus 3 cubed minus 2 times the square root of x plus 3 plus c. Any question or problem with that before we continue? Is it clear?
Yes, sir.
So what if I have the question, the one with the square root beneath as denominator? What if it's raised to power 2, that x?
Okay. It's the same thing we are going to do. So if you have x plus 2 over, so is this what you mean? X plus 3 squared. Is this what you're saying?
No, sir, I'm saying square root of x squared plus 3.
X squared plus 3. Interesting. Okay, so to do this, then this will have to be broken down into x over square root of x squared plus 3. U substitution will work on this part. But the main problem will be the other guy. 1 over square root of x squared plus 3. So I'm going to do the left-hand side, but the right-hand side, we are going to peg it for now. Because this one will require some substitutions it's not U substitution. It's going to be a trig substitution. In fact, probably an hyperbolic trig substitution. But for the one on the right, you can just go ahead and say, well, let U be equals to x squared plus 3. Then the U dx will be 2x. Okay? So, and that means that our dx is equal to du over 2x. So it means that x over square root of x squared plus 3 with respect to x is equal to the integral of x over square root of u times du over 2x. And then the x cancels the x. We are going to be left with 1 over 2 integral of 1 over square root of u times du. And we have done the integral of 1 over square root of u. It is 2u, yes, 2 square root of u. So this is 1 over 2 times 2 square root of u plus c. So that will be square root of u plus c, which is square root of x squared plus 3. But this other part is not an elementary one. Okay, so we are going to peg it for now. Maybe at another time I can just write it out and send it to you. Okay?
Okay, sir. Thank you, sir.
Yeah, you're welcome. So assuming the plus 2 is not there, then the answer would have been just this. But the plus 2 makes it takes it up a notch. So we are done with number 1, these questions. So let's go to the next. So we have done this. So let's move on to something. Yeah.
Yes, sir. So, I want to ask, let's say I have a function like x cube minus x squared plus 2 over x squared minus 1, for example. Can I just do polynomial like division on it if I have a remainder of 0? Can I now like find the integral of that value instead?
So is this what you are saying?
Yes, something like that. Yes.
So yes. So you remember I said when you have a fraction and you have an improper fraction, you have to do long division. So where is it? Yeah, improper fraction, you have to do long division. So this could fall, this is definitely a case of what you have here. So you would have to do a polynomial division. So but before you do polynomial division, it is advisable for you to break it down into pieces first. So x cubed, so you can do x cubed plus 2 over x squared minus 1, then minus x squared over x squared minus 1. In both cases, you will need polynomial long divisions to break it down into something plus something over x squared minus 1. Then again here, something plus something over x squared minus 1. Then you integrate. That is usually the idea for an improper fraction like this. Okay. So because I want to do something very similar to what we've been discussing, so instead of going to number 3, I would want us to look at number 6 because it's similar to the question Yinka asked just now. So x plus 1 cubed over x squared plus 1. X plus 1 cubed over x squared plus 1 dx. Let me see it again. Is that what is there? Yeah. All right. So does anybody have an idea of how we might handle this? There's one thing about integration is that, the more you practice, the more you get intuition as to what could be a possible way to solve things. Does anybody have an idea of what we can do?
So before I say my idea, I want to ask a
Okay.
question. Will
All
this
right.
thing lead to tan inverse?
There will be
Like,
yes, there will be a tan inverse somewhere there.
okay, I don't know.
There will be a tan inverse somewhere there. So anybody with an idea, just whatever comes in your mind. I want people's ideas. What do you think when you see something like this? What is your first thought, or what do you think?
I feel like that for the numerator, I can break it into x plus 1 bracket x squared plus 12 plus 1. And then for the denominator, I can do difference of two squares and then I will cancel out 1 x plus 1. Would that be possible?
Okay. Okay. So that is a nice attempt, although that will not work here because the denominator is actually not x. It's not a difference of two squares. Can you see? The denominator is not a difference of two squares. It is a sum of two squares. So x squared minus 1 is a difference of two squared. That is the one that will give us x minus 1, x plus 1. But x squared plus 1 is not a difference of two squared. This one is actually x plus 1 squared minus 2x. So that method might not work. But this method now is closely related to what Eva just said here. So the first, okay, favor, I can see your hand. So you just go ahead and unmute and talk. Don't worry, you can always interrupt me. I'm okay with that. So, Favor, what do you have to say?
Okay, so what I think is that it's going to lead into partial fractions. So you're going to like divide the denominator with the numerator. Then from there you do your partial fractions.
Okay, that's a nice idea. However, we partial fractions do come in when you have a denominator that can be broken down. So, for instance, if you have x times x squared plus 1 in the denominator, then you need a partial fraction to write this as a over x plus b over x plus d, bx plus c over, x squared plus 1. But not everything that you said is a waste, because we can. So the first thing, just like Eva, I was saying, the first thing we would like to do here is to actually see x plus 1 cubed in its full glory. And it's going to look like almost whatever I was suggesting the other time. So what is x plus 1 cubed? That is x cubed plus 3x squared plus 3x plus 1 over x squared plus 1. I hope everybody is comfortable with actually getting that expansion. Is there anybody here that cannot do that expansion? Something I can quickly go over. Anybody here that is not comfortable with doing that expansion? Okay. So there are different ways to see the expansion. You can either just write out x plus 1, x plus 1, x plus 1 and do it the naive way. Or you can use the usual Pascal triangle stuff. Okay? Because this is x cubed plus x squared plus x plus 1. Then we have 1, 1, 1, 2, 1, 1, 3, 3, 1. So this is 1, 3, 3, 1. So that being said, we can already see that so we can do long division, and we can also try to be creative here. So when I say long division, you can do something like this: x cubed plus 3x squared plus 3x plus 1. Then you divide by x squared plus 1. Well, I don't know. So I'm actually seeing some creativity that can be in play here. So if you group well, so I can group as I'm coming. Let me see. If I group, okay. If we group 2x minus 2, that will not work. I'm being over ambitious. So let's do the number division. The x squared in x cubed is x. Then that would be x cubed plus x. We subtract and we get 3x squared plus 2x plus 1. X squared in 3x squared is plus 3. Then we have 3x squared plus 3. Then we subtract and we'll be left with 2x minus 2. So I was being over ambitious with trying to group it. Grouping will not work there. Although I can see something that could have done, but let's just go direct here. So this is quotient plus remainder over the divisor. So that would be x plus 3 plus the remainder 2x minus 2 over x squared plus 1 dx. Is anybody confused with any parts of what we have just said? So if it is clear, then we can actually go ahead with this. So we know that this can be split into x plus 3 dx plus 2.
Okay, sir.
Yeah, yeah. Oh,
There's yeah. Contact message.
Adedayo, you said, all right. So which part? You can unmute yourself and ask which part is unclear. Okay, he's typing. So maybe I should go over that slowly again. Okay, so this deletes, this deletes. So let me clear this and clear this. Okay, so the question was x plus 1 cubed over x squared plus 1. The first thing I said we should always think about is to think about whether we can simplify. Or so, and this one is not something you can simplify. Also, use substitution. Can use substitution work here? I don't think so, because by the time you say the ideal substitution would have been u equals to x squared plus 1. But this will not help us, because by the time we find the u dx, we'll get 2x. 2x will not cancel anything in this numerator. So that means we cannot continue with u substitution. So we have to do something else. And to do something else means spread everything out. Let's see what it is. So we've started with expanding x plus 1 cubed. So to expand x plus 1 cubed, you can either do x plus 1 times x plus 1 times x plus 1. So you do these two first. You get x squared plus 2x plus 1, and you multiply it with x plus 1. Or I said you can use the Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. So x plus 1 cubed is always just going to be x cubed plus x squared plus x plus 1. Then you put the 1, 3, 3, 1. So that is the x plus 1 cubed. And that is why we have the numerator to be as this. Again, we could have said, all right, from here, let us start splitting it into x cubed over x squared plus 1, then plus 3x squared over x squared plus 1, plus 3x plus 1 over x squared plus 1. Again, this will not help us, because the denominator is still an improper fraction. Still an improper, all of them except the last one. So, and to avoid doing all of those, we need to break it down. Anytime you have an improper, for instance, if you have 7 over 2, you can write it as 3 plus 1 over 2, where 3 is the quotient, 1 is the remainder, and 2 is the divisor. So that's the idea. Anytime you have improper fractions, the main idea is to first and foremost break it down first. So to break it down means we do the long division, just like the 7 over 2. So we are dividing x cubed plus 3x squared plus 3x plus 1. We are dividing that by x squared plus 1. So to do long division, you take x squared in x cubed, that is x. Then you do x times this everything here. So x times x squared is x cubed. X times plus 1 is plus x. So I write it under 3x. Then we subtract. So when we subtract, this cancels this. 3x squared comes down. Then 3x minus x is 2x. And the next thing is, again, x squared in 3x squared is plus 3. Then we multiply again. Multiply 3 by everything here. That gives us 3x squared plus 3. So the plus 1 here can come down. So if we subtract, this cancels this, the 2x comes down, and 1 minus 3 is negative 2. So it's just like the case of 7 over 2. So this is like the 7 here, this is the 2 here, this is the quotient here, this is the remainder. So it means that this fraction is the same thing as x plus 3, that is the quotient, plus the remainder, which is 2x minus 2 over x squared plus 1. Now, when it is in this format, it is easier to deal with because we know the integral of x, we know the integral of 3. As a matter of fact, if I write it as x plus 3 dx plus I'm tempted to factor out the 2 there, but let me still write it this way, plus 2x minus 2 over x squared plus 1 dx. Of course, we know that the integral of x is x squared over 2. And the integral of 3 is 3x. But this other side, we need to be careful. So first and foremost, I can also split that side into x over x squared plus 1. And, okay, then let me jump for it to be clear. 2x over x squared plus 1 minus 2 over x squared plus 1 dx. Then this one can now be split into 2 into bracket x over x squared plus 1 dx minus 2, 1 over x squared plus 1 dx. So as Yinka predicted, we are going to have arc tan x for this last side because that is 1 over x squared plus 1. The integral of 1 over x squared plus 1 is arc tan x. So we already know this to be arc tan x. So we now need to deal with this.
Sorry, sir. Sorry.
Yeah.
Sorry. How did you get your integral of x plus 3 to be x squared over 2 plus 3x?
Okay. So what is the integral of x? Let me throw that back to you.
The integral of x is x squared over 2.
What is the integral of 3?
The integral of 3 is meant to be 0, is it not?
No. The derivative of 3 is 0. But the integral of 3 is 3x. Okay? So when you differentiate 3x, what is the differentiation of 3x?
3.
So if the differentiation of 3x is 3, integral of 3 must be 3x. Because it is always word and opposite. Okay?
Okay.
So generally, the integral of a constant is constant times x raised to power 0. And if you use the reverse power rule, this is cx 0 plus 1 over 0 plus 1. That is cx. Okay?
All right. Thank you, sir.
So the derivative of a constant is 0, but the integral of a constant is constant times x. So then we are now going to concern ourselves with the integral of x over x squared plus 1. And in this case, dx. So let's assume this is just the question you are faced with. What is the first thing that should come to your mind? Does anybody have an idea? So the integral of x over x squared plus 1.
Use substitution.
U substitution. With what u? What u should you use?
X squared plus 1.
Exactly. So
Yes.
if we have u equal to x squared plus 1, if we have u equals to x squared plus 1, then the u equals to 2x dx. Then it means the x is equal to the u over 2x. That means we can write this as x over u times the u over 2x. So the x's cancel out. So we are left with 1 over 2 integral of 1 over u du. And we know the integral of 1 over u.
Sir,
We
I
know
can't
that is...
see what you're doing currently.
Okay, did you just join back?
No, no, I've been on the call.
Okay,
I don't know if it's just me, sir.
I think it's just
I
you,
can't.
but
No,
I
I
also can't see
can't.
it.
you can't see it. All right, no problem. That's okay. I'll just stop sharing and share again. Oh, nothing now. No, Forest in no Aston Villa. Sha. All right, so let me um stop sharing.
Okay, it's now showing, sir. It's now showing.
Is it showing for everybody now?
Yes.
All right, beautiful.
Yes, sir.
Good. So integral of 1 over u is natural log of u. Then we know that u is x squared plus 1. So x squared plus 1. So we can now plug that into this place. So this is x squared over 2 plus 3x plus 2 times 1 over 2 natural log of x squared plus 1. I don't need to put the absolute value because I know x squared plus 1 is always going to be positive. Then minus 2 tan inverse of x plus c. So finally, the 2 cancels the 2 here. So we have x squared over 2 plus 3x plus natural log of x squared plus 1 minus 2 tan inverse of x plus c. That is the answer to that question. Is any part of this unclear? Good. Good. So let's move on. So let me see. Prop. So we've done this and we've now done this. Let's do the next one here. Again, it's a fraction. Natural log of x minus 1 over natural log of x squared dx. In this case, you can actually see that we can split this into, 2 parts, right? We can split this. I hope I won't run into trouble here. I have not thought about this question. Let me see. So this is if we make x u to be equal to natural log of x from here, that will not work because the x will show up. but we can split it up into natural log of x over natural log. If this does not work, I will go to another question temporarily while I still think about this one. So the first part is 1 over natural log of x. And the second part is 1 over natural log of x squared. This is strange. This is strange. Let me think about it. I won't want to waste time on the call while we are thinking about it. So 1 over natural log of x. One over natural log of x. So if we have something like this, how do we go about it?
Sir,
Yeah.
I don't work, but the way you did that one, that you made u equals to something. So we can make u equals to ln x, then put u on this, and maybe cancel out also the numerator. I mean,
If you make u to be equals to ln x, you are going to have u minus 1 over u squared. But where the problem will come up is the x, if u is equals to natural log of x, the u dx is equal to 1 over x. Then it means that dx is equals to x du. So there will be an x that will not go away. Okay? So I have actually thought of it forward some steps. So I'm coming. It doesn't look like an elementary function. Hold on. So if we do that, will it work? It is not an. Oh, okay. So let me try another approach. Oh, okay. If we do that, it is not an elementary function because you are going to be getting something that is outside the scope of. How does it want you to do this? I know this is Egwe's work at play, but how does it want you to do this without getting an error function? There's going to be an error function here. Oh, no, it's not an elementary integral. Because the integral of 1 over natural log of x, this guy here is something like, and I'm very sure you people have not heard about that. So it's an EI natural log of x. While this one is also EI natural log of x plus 1 over x over natural log of x. So I'm going to pend this one. Okay, so I'm going to peg it. Now we don't waste time thinking about it. Then if maybe before I sleep, if I think about an easy way to think about it, I'll write it out and send it across to you guys. All right, so we can come back to the other ones. So number 3 here. Oh, number 7 is, I think that one is quite much easier. So the integral of 2 to the power of x over square root of 1 minus 2 to the power of 2x dx. before we continue on that, so we have just written an integral of 1 plus x squared. Does anybody remember what we said it is? What is the integral of 1 over
Sorry,
x
sir.
squared?
Is it one over 1 plus x squared or 1 over x squared?
1 over 1 plus x squared.
That's tan inverse of
Means
x.
like tan inverse of x.
Good, tan inverse of x. What about 1 over square root of 1 minus x squared?
That's cos. Is it cos or sine?
No, fine.
Sine inverse of x.
Sine
Fine.
inverse. Okay, good. So the reason I'm asking this is it's actually looking like that is what we want to do next. Can you see it? So for this question, what will you do?
We factor out 2 raised power x.
So you cannot factor out 2 raised power x because it is not a constant. You can only factor something that does not contain x. So any other idea? Yinka, what do you think?
These questions are they test or exam questions by because
Yeah, test questions. Yes, Joy. Use substitution. Thank you. So when you see a complicated question, try to use a use substitution to change it into something that is not so complicated. So Joy, what will you make as your U if you think it's a use substitution? So let's make you can see what I wrote here. You can see that if by the time you make, U equals to something, it is going to, do you agree that, okay, let me just do it. So U equals to 2, let's say U equals to 2 to the power of x, right? So if U is equals to 2 to the power of x, what is 2 to the power of 2x? That is U squared. Do you agree? And what is the U dx? Does anybody know? If U equals to 2 to the power of x, what is the U dx?
To the power of x
So you said
into
Thank you.
linked
So 2 to the power of x times natural log of 2. So if U is equals to 2 to the power of x, then 2 to the power of 2x is U squared, and the U dx is 2 to the power of x natural log of 2. Then it means we can rewrite the x as 2 to the power of x, but 2 to the power of x we said is U, so that means that is U ln 2. So it means dx is equals to du over U ln 2. Then we can rewrite our question as integral of U over square root of 1 minus U squared times, then instead of dx, we are going to have du over U ln 2. Can you see where we are going? What is the next thing that will take place here naturally?
u over 1 square root of 1 minus u square is arc tan of u, arc sine of u,
Not
like
really.
tan inverse of u.
No. That is, it is not U over that. It is 1 over square root of that. That is arc sine.
Yes. Sorry, sir.
But you are along the line because the next thing I would have expected you to say is that U cancels U. So in most cases, when you do U substitution, at some point things have to cancel out. So, and if that happens, we can also factor out the constant here. So this is the constant that can come out. 1 over natural log of 2. Then integral of 1 over square root of 1 minus U squared times du. And from what we said, that integral of 1 over square root of 1 minus x squared with respect to x is arc sine x. So it means this one will be 1 over natural log of 2 times sine inverse of u plus c. So our answer is 1 over natural log of 2 times sine inverse of 2 to the power of x plus c. Is it clear?
Yes, sir.
And in this u equals to raised to power x, all that plus the differentiation. The integration is clear, yes. Just the differentiation and shall you manipulated, yeah.
Which part? Which part? Which part? You mean this one here?
We already got the differentiation of that u, but
Mm-hmm.
u squared, you now change something to u, is what I don't understand.
Okay, so u is 2x, that is clear, and its differentiation is 2 to the power of x natural log of 2, right? Then, because u is equal to 2 to the power of x, so instead of saying 2 to the power of x natural log of 2, we are saying that is u ln 2. Then also, 2 to the power of 2x is the same thing as 2 to the power of x raised to power 2. So that means 2 to the power of 2x is u raised to power 2. So if the u dx is 2 to the power of x ln 2, and we are saying since 2 to the power of x is u, that would be u ln 2. We can now rewrite dx as du over u ln 2, right?
Yes, sir. Now, okay, I thought you did something to the 2 raised to power 2x. It was only like u raised to power 2 that you did. I thought
Yeah,
some.
I just changed it to u squared.
Okay.
All right.
Sir.
So we are done with number 7. And number, so because of time, I know people will want to start going to sleep. So 5 and 9, and we'll close it up. I think we can do, let's start with 9, unless it's another non-elementary integral, but let's see. Integral of 1 over x ln x ln x. Interesting. Interesting. Okay, so again, of course, we know that it is u substitution. So you can go ahead and say u is equal to natural log of x, but I want to take a bolder step and say u is equals to natural log of x. I think that will work. And if it doesn't work, we'll come back to this natural log of x. So yeah, because by the time we take, I have seen the derivative, looking at the derivative, I think it will help to cancel things out easily. What's the derivative of natural log of x? What is the derivative of natural log of natural log? What is the u dx? So generally, when y is equals to natural log of a function, the y dx is just the derivative of that function over that function. So in this case, the u dx will be the derivative of natural log of x, which is 1 over x, over natural log of x. Can you see why I used it now? Because this is just 1 over x ln x, which is exactly what we have here. But like I said, one could have used u equals to ln x. I think that will also work. But it means you have to do u substitution twice. So if the u dx is 1 over x ln x, then that means du is equal to dx over x ln x. And that's exactly what is here.
I'm not seeing what you are seeing, sir.
Oh, the screen is not showing.
Hello, sir. And the derivative of ln x.
Yes.
I don't understand, sir.
Okay. Let me go slower there. Okay, so again, if y is equal to natural log of stuff, the y dx is the differentiation of stuff over stuff. Or let's just use chain rule directly. Okay, because this is chain rule. So let's do chain rule directly. Y is equal to natural log of x. Yinka, can you actually see the screen?
Yes, I can see the screen. I don't just understand what you are saying, sir.
Okay, that is what I'm going. I'm doing it over again. So y equals to natural log of x. So let u be equals to natural log of x, the inside one. Or maybe it was too big a step to take for you people. So let's u be equals to natural log of x. Are you okay with that? So then what is the u dx? The u dx is 1 over x, right? Then it means dx is equal to x du. Right? Is this one clear?
Yes, sir, it's clear.
So this is now going to be equal to x du over x times u times natural log of u. Because we have said u equals to natural log of x. So this will give us this, and this will give us this, while this is this. Okay? Then the next thing is for x to cancel x. And you will be left with integral of du, or let me write it this way, 1 over u times ln u du. So this is now like a different question. So if you have integral of 1 over x ln x dx.
Your screen has paused again.
Okay. Okay. Let's see. What about
Okay.
now?
Yeah, it's back now. It's back now.
Okay. Okay. So good. So if you have 1 over x ln x, if this is just if this is the original question, what would you do? Of course, we know that this is going to be a u substitution. It's different from when you have integral of x ln x. This one has to be integration by parts. But when you have 1 over x ln x, that has to be u substitution. So if we do u equals to natural log of x, so that is why I'm going to come back here and say, all right, so let v be equals to natural log of u. I'm supposed to be using absolute value there, but let's just overlook it. So if v is natural log of u, so you are doing u substitution again, but v substitution this time around. Then dv du is equal to 1 over u, which means that du is equals to u dv. Inka, is it clear?
Sir, I believe your screen has paused again.
That is
Okay.
strange. Very strange.
Just come now.
All right. Yinka, I hope you are not asleep yet.
No, not.
Okay, so do you understand up to that point?
Yes, I do.
So we can rewrite this integral as, so instead of du, that will be u dv over u times, so our natural log of u is now v, so u times v. So u cancels u. That is integral of 1 over v dv. So to avoid doing the u substitution twice, that was why I started with taking my u to be natural log of x. So that means I have combined, this u substitution and this v substitution together. So ordinarily, you people had problem with taking the differentiation of natural log of natural log. Let me explain that, how to take the derivative of that. So if y is equals to natural log of x, I think the screen is paused again. It's in red.
Yes, sir, it's
Microsoft.
frozen.
Yes, it's in red. Microsoft Teams now. Yeah, I think it's back now. So if y equals to natural log of x, how do you take the derivative of this? You say let u be equals to natural log of x It's not freezing on my own side here, but I can actually feel that it is freezing there.
It's back now, sir.
Okay. So u equals to natural log of x, then it means y equals to natural log of u. Then du dx is 1 over x, and dy du is 1 over u. So using chain rule, dy dx, which is equals to dy du times du dx, is equal to 1 over u times 1 over x. That is 1 over xu, and that is 1 over x natural log of x. That is the derivative of ln x. So again, let me remind you, if y is equal to ln of any function, whether it is also ln x or sine x, the y dx is equals to f prime, you take the differentiation of that function over that function. For instance, natural log of sine x. The differentiation is equal to cos x over sine x. Okay? Good. So the integral of 1 over v is natural log of v plus c. Then we remember that v is natural log of u. So that is natural log of u plus c. Then we remember again that u is equal to natural log of x. So the answer is natural log of natural log of x plus c. Is there anybody that does not understand that? Is it clear?
I would have said
Yes,
it's
sir.
clear, sir.
Okay.
But can you come
Yes,
again?
sir.
Parts.
Which part?
Natural log of x plus c.
So the integral of 1 over v is natural log of v. Well, what is v? V is equal to natural log of u. So that is natural log of u. Then we remember again that u is equal to ln x. So we can rewrite this as natural log of what is u? Natural log of x plus c. Is it better now? Good. One last one before we go. I'm beginning to get tired as well. So let's see if I can do number 5. Because it looks as if, so I'll tell you what to do with 3 and 4 yourself. So integral of x squared minus 2. Why didn't I pick an easy question? Dx, then x to the power of 4 plus, okay, maybe I should just, so that I don't continue to scroll back and forth. X to the power of 4 plus 5x squared plus 4 times tan inverse of x squared plus 2 over x. Where do we even start this one? Very well done. Okay, so definitely we know it's going to be a u substitution. That is something that is sure. But picking what the u will be is the tricky part. We cannot pick u to be x raised to power 4 plus 5x squared plus 4, because if you take the differentiation of that, you are going to get something that has cubed. And there is no cube anywhere here that would help us. We cannot take x squared plus 2 over x for almost the same reason. We cannot use x squared minus 2. But something we can try is u equals to the whole of this guy. That is the only thing that we don't know what the differentiation is directly. So if it works, we are lucky. If it does not, maybe we'll just call it a day. So u equals to tan inverse of x squared plus 2 over x. So we need to take the derivative of that. Eva, do you know how to take the derivative of tan inverse of x squared plus 2 over x? How to take the derivative generally of inverse tan functions?
It's going
Eva,
to be should I say it's going to be an implicit function? No, it's not implicit, but it's going to be tan u equals to x squared plus 2 over x.
yes, I like that. So this is tan u is equal to x squared plus 2 over x, which is actually, this is actually, what is x squared plus 2 over x? That is x plus 2 over x, right? Then I can differentiate both sides with respect to x. The differentiation of this left-hand side is sec squared u du dx. And the differentiation of the right-hand side is 1 minus 2 over x squared. Then it means that the u dx is equal to 1 over sec squared u times x squared minus 2 over x squared. But what is sec squared u? Sec squared u should be 1 plus tan squared u. It means that sec squared u is equal to 1 plus, we know what tan u is. Tan u is this x squared plus 2. So tan u is x squared plus 2 over x. So sec squared u is 1 plus x squared plus 2 over x squared. Interesting. And that is
Sorry,
going to
so
be, yeah.
okay. I wanted to ask something, but I've realized where
Okay.
the square is coming from.
Okay. Then we have this to be 1 plus x squared plus 2 squared over x squared, which is equal to x squared plus 2 squared over x squared. So if this is sec squared u, then we know what 1 over sec squared u is. So 1 over sec squared u will be the reciprocal of this, which is x squared over x squared plus 2 squared times x squared minus 2 over x squared. Interesting. Du dx. So x squared cancels x squared, right?
Excuse me, sir. I'm kind of lost from the step just before this one.
Okay. Let's go over this again carefully. So you agree that if u equals to, yeah, somebody asked for the recording. Yes, there is going to be, after this class, I'm going to send I think I'm going to send a link to whoever. So tan u is equals to x squared plus 2 over x, and sec squared u the u dx is equals to, if you differentiate x plus 2 over x, you get 1 minus 2 over x squared. Then we said the u dx is equal to 1 over sec squared u times, so 1 minus 2 over x squared is x squared minus 2 over x squared. Then what we now did was to get an expression for sec squared u in terms of x. So since we know that tan u is equal to x squared plus 2 over x, then it means that tan squared u is equal to x squared plus 2 over x squared. Then we know from the Pythagorean identities that sec squared u is equal to 1 plus tan squared u. Then that means that sec squared u is equal to, yeah?
Okay. Shouldn't tan square u be the whole expression all squared?
Yes, that's what I did.
Exactly.
This should be squared. Yeah.
I mean,
Thank you for that.
yeah.
So tan u is x squared plus 2 over x. So tan square u is x squared plus 2 squared over x squared. So the whole expression squared. So I just broke it down into numerator and denominator. Okay?
Okay, sir.
So this is what it should be: x squared plus 2 over x, then all squared. But this is the same thing as this. Right? So I split the square for the numerator and the denominator. Then it means that sec squared u is 1 plus x squared plus 2 squared over x squared, which is the same thing as x squared plus x squared plus 2 squared all over x squared. As a matter of fact, I can expand that numerator to be x squared plus x raised to power 4 plus 4x squared plus 4. Can you see where I'm going? All over x squared. So if this is sec squared u, then 1 over sec squared u will be x squared over x to the power of 4 plus 5x squared plus 4. Can you see something? Beautiful. This is equals to this. Then times x squared minus 2 over x squared. And by the time this cancels this, we are going to see that this here is also equals to this. Interesting. So it means that, so if this is the u dx, so is it clear now up to that point?
Yes, it is.
So if this is the u dx, then we know that dx is equal to, say, turn it upside down, x raised to power 4 plus 5x squared plus 4 over x squared minus 2 du. So it means that the integral will now be given as x squared minus 2 over x raised to power 4 plus 5x squared plus 4, then times u, because that is what we made as our u, this guy, then times dx, which is x raised to power 4 plus 5x squared plus 4 over x squared minus 2 times du. So we bring out our cutlasses, cancel this, and we are left with integral of 1 over u du, which is natural log of u. So it means our answer is natural log of tan inverse of x squared plus 2 over x plus c. Sharp. So that we can go now. Let me just tell you what you need to do with number 3 and
Sorry,
number
sir. Please, can you go back to the question, to the answer, to just please? Okay, thank you, sir.
You're welcome. So for number 3, it is going to be number 3 is going to be a u substitution. Let u be equals to 1 minus x. Then you say x is 1 minus u, x squared will be 1 minus u squared. So the numerator will be 1 minus u squared. The denominator will be u raised to power 2024. You can now split the numerator to be 1 minus 2u minus plus u squared over u to the 2024. Then you can give 2024 to all of them. So that is how to do number 3. So you can try your hands on that. If you don't get it, so let me know. For number 4, we use so what is cos 2x minus 1, or what is 1 plus cos 2x? So we know that cos 2x is equal to 2 cos squared x minus 1. So cos 2x plus 1 is equal to 2 cos squared x. Similarly, cos 2x is equal to 1 minus 2 sine squared x. So if I bring minus 1 to the other side, cos 2x minus 1 is equal to minus 2 sine squared x. So you have the numerator to become minus 2 sine squared x, and the denominator to become 2 cos squared x. So the question is the same thing as sine squared x over cos squared x. So think of a way to finish that from there. If you cannot get it, you let me know. I can write it out tomorrow. Any other question, general question before we call it a day? Any general question?
Sorry, sir. Please, can I see like the past questions you solved earlier?
Yeah, it is. So this is it. This is it. It is the one we are still working on. I will send it.
Yeah,
I will send
um,
it to you. Okay.
I think so.
You're welcome. So I just sent it to you on WhatsApp. So we're going to stop there now, and I'll try to upload the video, or just send you the link. And yeah, I think Eva will distribute it to people that are involved. So if there are no any other questions, then we'll call it a night. Have a good night, all of you.
Thank you very
Thank you
much,
very
sir.
much,
Good
sir.
night.
Thank you very much,
Yeah.
sir.
Thanks, sir. Good
Yeah.
night.